Alright students, this video we're going to talk about the law of sines again. And this one I'm actually going to show you where did it come from. Now, I want to show you this. There's a lot of good websites online. This is from mathisfun.com. They, of course, have the law of sines right at the top. Very good, easy to read graphics, and then it goes through and does several examples. Okay. This is what we want to talk about. Where did it come from? And their example's pretty good, but it might be a little bit confusing how there's a step in there that's kind of a little bit not too clear. So that's what we're going to do in this video. We're going to explain how do you get from this to the, did it just come by magic? That's really the question. Is this magic? Because you might look at something like this and say, did someone just, think about it for a while? You know what? I think this might be true. That's not exactly how it came up. And what's nice about it, though, is it works for any triangle. That's really the power of this, any triangle. And the proof will show you why that's true. So the proof is very, very important to sort of understand why things work. All right, let's get started with the proof. So we start with the generic triangle ABC, and we don't even have any angle measures or side width. The point is this works no matter what size, what the angles are. What we do need to do, though, is we do need to add our own special thing. You're allowed to do this. We'll say we'll draw in an altitude. An altitude is something that exists in math. It's well defined. We're allowed to draw it into any triangle if we want to. All right. Let's call that altitude H. Alrighty, and what we're going to do here is we're going to try and write a relationship between H and A and C and B. How can you write a relationship if there's no numbers? Well, there's no numbers, and that's the whole point. There are side lengths, though. Across from A, this side would be little a. Across from C, this side would be little c. And across from B, this whole big side would be big B. Okay. We probably won't need all of them. Let's set up one of them. Okay. So let's sort of cover up part of this triangle here, ignore sort of that part of it, and say, okay, if we just want to write a relationship between A, H, and C, I bet there's a relationship between A, H, and C. What I mean is from A, H is the opposite side, and if you're looking at just this triangle here, we'll shade it in, of this triangle here, we now have a right triangle, and H is the opposite side, C is the hypotenuse. See if you agree with that. So if you agree with that, we should be able to say the sine of A is opposite of our hypotenuse, H over C. Okay. Or if you multiply both sides by C here, times C, these will cancel. This will be C times the sine of A equals H. H. Sorry about that. Let's make that a little bit nicer. There we go. H. Alrighty. Next, let's do that same thing with the other part. If we did this side here, let's cover up all this work here. We'll come back to that. It might not make sense why we did that yet. Let's come back to it, though. If you look at this side here, you could say that the sine of C would be the opposite of our hypotenuse. Opposite of our hypotenuse. And if we do the same trick to get H alone, if we multiply by A on both sides, those will cancel. You got A times sine of C. Now, that's the key. Here we go. You say, well, wait a minute. You said H was equal to this, but you also said H was equal to this. Well, if H equals both those things, then these two things must equal each other. C times sine of A must be equal to A times sine of C. And that in itself would be kind of nice. It's a nice little theorem, but we can write it a little bit nicer. Okay, let's just make sure we got that. It's like saying H is equal to 10, or H is equal to 5 times 2. Those are both the same. So 5 times 2 equals 10. Okay, so these are both the same. H is this, H is that. Well, this and that are the same then. If H equals both these things, they're both equal. All right, so if you don't agree with that, that is the transitive property. You can look that up separately, but that we use this a lot. We essentially did a substitution here. We said this is equal, so let's plug it in. All right, we're finally there. What we want to do is get rid of these things. You're allowed to divide on both sides as long as you divide by the same thing. You can divide by 10, divide by 2, or let's divide by AC. What'll happen here is h times c is just a number. That could be 5 and 2, it could be 7 and 3, doesn't matter. This c will cancel with this c. This a will cancel with that a. And what you're left with is a over a sine c over c. That right there is the law of sines. You say, wait a minute, that looks different. Well, the way the book wrote it, and the way I prefer to write it, is flip-flopping it. So if these are equal, then it would still be equal if you flip-flop both of them. If you do the reciprocal of both of them. And that right there is your law of sines. We proved it, it didn't take too many steps, and now you know it's true for any right triangle. As you'll notice, this whole proof, we didn't use a single number. Congratulations, guys. You are now doing high-level math proofs, proven big, mega stuff like the law of sines. Congratulations, guys. You worked hard. You made it through. That's your first really awesome formal proof without actually any numbers. Good job.